Hello everyone! This is second part of video Why Algorithms, and we will discuss binary heap data structure, effective algorithm for its implementing, and where it can be used. Studying of algorithms by yourself, especially from scratch, may look very bulky, with lots of unstructured, non-aggregated information. It would be much better to start seeing patterns, to understand most important directions to start working with, types of algorithms and related supportive data structures in each direction. It would be also great to see few examples how on practice such algorithms can be used, which use cases, scenarios such algorithms can help solving. In the videos What Algorithms, we started with first group of algorithms, sorting algorithms, with merge sort and quick sort examples. We also provided use cases, like finding three smallest numbers in a set, or geometrical task, convex hull, where sorting plays central role. It turned out that there is a specific separate second group of subtasks, once decomposed, which require to periodically know the largest or smallest element in a resizable set of values. Let's think about possible use cases for this group. For example, to find m largest or similarly m smallest elements in a set of n items. One example is to find 5 largest salaries of 1000 employees team. You can decompose this task the way you can take out the largest salary 5 consecutive times from list with all salaries. Each time you retrieve the largest value, you remove it from a list, not to take 5 times the same largest value. We can bring another not obvious use case, like similarly we brought sorting subtask for convex hull task in the previous video What Algorithms. For example, if we plan to simulate natural phenomenon, graphically mathematically simulate collisions of n moving molecules, each of them moving with its own speed, having different size and mass. When they collide with each other, or with the walls, if we have closed space, they change their trajectory and velocity, which can be mathematically calculated according to laws of elastic collisions. Imagine lots of molecules are constantly flying. How to take care of all calculations and proper molecules paths? Easiest brute force model is to track their positions every movement, every certain amount of time. But tricky parts are, this approach considered not continuous but discrete movements, and if you have a large time interval between tracking positions, like 1 second, there might be a chance that two fast-moving molecules with crossing paths might change their positions too far, and we may miss moment of collision. Or, in contrary, we can take too small time interval, 1 millisecond for example. In this case, there will be huge amount of calculations. What if you have thousands, millions molecules? Your computer may not have enough computational power. Therefore, totally different effective approach can be used. Constructing a list of collision events, particle to particle and particle to wall. Then prioritizing events by time. So each time we know which event to happen the earliest among others. That means between collisions, molecules move straight line trajectories. We focus on time only when collision happens. Once it happens, we can do some actions, like calculating new trajectory and velocity of collided particles, removing this event from our queue, thus having the very next event in time ready. Update list of events, because new trajectories may cross other molecules' paths, so we may need to add some, and so on. We can name such use case as event-driven simulation, when events are ordered in time. If we search for such largest, smallest item just one time, sorting algorithm can be used once prior to that. But what if you have dynamically changing set of elements and periodically from time to time need to check few largest or smallest items while adding not sorted items between searches? Apparently, using sorting each time might not be efficient. But our priority queue data structure, discussed in first Why Algorithms video part, would be a good helper. Remember, for example, del max function, which returns and deletes the largest element from priority queue? When it comes to implementation, it turns out that we can use several possibilities for low-level design intent. For example, we can use ordered set or unordered set of values underneath. But let me save your time searching for the best algorithm. Binary heap data structure turned out to be one of the most efficient and simple real implementation of priority queue abstract API. Let me briefly describe how it's designed and how it works. What is actually happening behind the wall with service window, which separates our API and implementation? And then we will compare its efficiency with ordered and unordered sets in terms of big O notation for each of three main operations. What is the magic of binary heap structure efficiency? For future algorithm experts, we need to introduce few terms. First of all, binary heap structure is based on complete binary tree underneath. Tree is a recursive hierarchical data structure. It has its root node and links to one or several disjoint subtrees. As you can see, description looped to itself, which allows by one line express great variety of different particular trees. For each tree, you can talk about levels of nodes. Nodes belong to the same level if they are at the same distance from a root. For example, all direct subtrees of a root node start on the same level. All the direct subtrees start on another own same level, and so on. Our tree depicted as inverted if visually compared with real trees growing from bottom root to the top leaves. But idea is the same. Every next branch is a smaller tree of the next level. Binary tree can have up to 2 links to subtrees on each node. Usually they are noted as left and right subtrees if both presented. Up to 2 links means that node may have just one subtree or even none. They say tree level is completely filled if maximum possible nodes are presented on this level. For binary tree, that means a level has exactly 2 subtrees for all their parent nodes. This level is completely filled. Complete binary tree is a tree which has just root node or all levels, except probably the last, completely filled by nodes. If last level is not fully filled, all its nodes are as far left as possible, like you can see in the picture. This tree considered as complete binary tree. A leaf is a node without any subtrees. Important property of complete binary tree. Every leaf is away from the root by the same distance plus minus just 1. Tree height is technically length of the longest path from the tree root to a leaf. Height of complete binary tree with n nodes is logarithm n. A logarithm explanation is out of scope now. Whenever you need to look for items from any leaf, bottom of a tree, till its root, top of a tree, you will spend a logarithm n steps, which corresponds to fast log n order of growth. Remember from previous video what algorithms. Tree structure becomes interesting when it's used for operations like searching, and for searching each node can store a value which named key. We'll see how keys can be used soon. We are coming to important term. Heap-ordered complete binary tree is a tree with 2 features. It has keys in all its nodes. Parent key is no smaller than children's keys, applicable for any parent key. How useful such structure can be? If any parent's key is no smaller than children's key, the more you travel towards tree leaves, the smaller key values will be. And on the other hand, which is more important, key at the root has the maximum value out of all keys in a tree. To be more precise, not smaller than any other key. Don't forget, we may have duplicate keys values. Max value of a root is essential for implementing priority queues operation to return maximum value from the list of all its values, preliminary goal for second group of tasks we are discussing. And such value is available immediately without searching, just looking to the tree's root. Quick reminder, heap-ordered complete binary tree implements priority queue. Let's look how efficient we can implement operations insert item and delete item. Remember, inserted item can have any value. Deleting is applicable only for the maximum value though, by a definition of priority queue specific operation. Analogically, remember about our funny unrealistic example of picky cashier who wants to take care of the tallest customer in line. Customers can join a line in any height order. but taking out customer will be only for the tallest one among them based on strange cashier's choice. Both operations, insert and delete, should not break the rule of our structure to have a parent's keys no smaller than its children's keys. And secondly, when we add new element to our structure at the end of operation, eventually we will have the leftmost place on the last tree's level occupied by some key to preserve complete binary tree structure as per its definition. The easiest and fastest way is to add new element at mentioned place at the end and then shuffle elements if needed. When we add new element at the end, we most likely violate heap order. Newly added value may be larger than its parent's value, but it is a temporary violation for the duration of insert operation. So we need to exchange newly added element with parent key and can continue changing recursively till possibly reaching the root. In this worst case, maximum cost of overall operation is 1 plus log n compares. Exchanging key with parent one allows us eventually eliminate temporary violation. By the way, I have a question. If you exchange newly added key with its parent and that parent has another child, could heap order rule be violated for that another child and its new parent? Of course not. Previous parent was no smaller than another child, and its place is taken by new item which can be only larger. Overall procedure is seen as adding new element to the end of the heap and swimming it up as air bubble in the water till some parent or maybe even root. For deleting from a heap, we also need to preserve complete binary tree structure and technically remove the rightmost element of the last tree's level. Efficient way of doing it is to exchange root with the last element and then remove the last element. Item on the top after that most likely temporarily violates the heap order, because it may be smaller than at least one of its child. To remove such temporary violation, we need to recursively sync the root. Such substep is about replacing it with the largest of two children, if any, till its children are no larger. Just FYI, since we're replacing with the largest child, which becomes root on each recursive step, then relationship with the new root and the other child still follows the rules of heap order. Overall procedure is seen as exchanging root with this last element, removing the last element, and sinking it down as heavy object in the water till it will be no smaller of its children's keys. Cost of overall operation is at max 2 multiply logarithm n compares. For simplicity, order of growth discards leading coefficients. Such coefficient does not change proportion between input data size and runtime. Remember from our previous video what algorithms. So order of growth of delete operation for a heap is a logarithm n. One more comment about delete operation. Once you deleted the max element, root node, its place in the root node takes the maximum element out of all elements left. So it's like a very fast operation to have maximum element always ready at the same expected place. Next thing, most likely if you read about algorithms yourself, binary heap may sound more familiar to you. Binary heap is actually array representation of a heap-ordered complete binary tree. Array is very simple data structure, allows to immediately access any item in array by its index by just one step. Remember our video about the data structures. It's like seeing numbered train cars. Once you see number, you can immediately reach and enter it. Binary heap can be implemented using array because of complete binary tree structure, which means that all levels, except possibly the last one, are full. Every next level, except possibly the last one, contains exactly twice more elements without missed elements in between. Therefore, we don't need to have links to children from parent node. We can just use arithmetic operations to find array index with immediate access to key value. To put keys of heap-ordered complete binary tree into array, array's indices start at 1, and we take nodes in level order, one level after another. It's always good to use imagination and for simplicity see our initial tree aligned to the right. To play in mind with tree's multi-level structure to fit into one-dimensional array. Arithmetic operations for parent-child relations are parent of node at k is k divided by 2, rounded integer. Children of node k are at positions of 2 times k and 2 times k plus 1. For example, parent of element at index 5 will be at index 2 equals to 5 divided by 2 and rounded to lower integer. Two children of parent item in index 3 are 6, 2 times 3, and 7, 2 times 3 plus 1. Here is a comparison table for order of growth of runtime for priority queue with n items. Here are main operations: insert, delete max, and max. Here are 3 possible implementations. And here are our big O's. There are a couple faster implementations, like one named Fibonacci, but they're very difficult for implementation. Among those implementations, which we mentioned in our table, how we can make an outcome that binary heap is the most effective. For example, we might be confused that for one operation, insert, binary heap is faster, but for another one, del max is slower. To clarify, we need to remember our order of growth graph from the previous video what algorithms. Can you see that on a large input data sizes, line represented log n big O is not growing significantly and relatively close to x-axis. So log n is not significantly slower than constant big O. It's like comparing two cars with a little bit difference in horsepower. But in the meantime, can you see log n order of growth is significantly faster than n? Here we compare usual car with super speedy racing car. Difference is obvious. Let's show it with numbers. For example, for 1 million nodes of a tree, you need to have maximum 20 steps to reach any leaf. 20 is the height of a tree, and mathematically 20 equals to logarithm of million. Which means that for binary heap, both operations insert and del max each can take number of steps proportionally to just 20 for input data with size of a million. For ordered array, even though del max operation will take constant time proportional to 1 step, but insert operation will be proportional to 1 million steps for the same input data size of million items. In the worst case, you may need to insert element at the beginning, if new elements is the smallest one, and then move each of existing 1 million items one place to the right. Usually, when you implement program, you do not use just one operation. For example, algorithm is usually useless if you just insert items into a set, but not retrieve, delete items from such set. There are usually several most often operations used. Imagine that both insert and del max are used equally in our priority queue. In our example with million items, for one insert and one del max, binary heap algorithm with tree underneath will use number of steps proportional to 40, 20 for insert and 20 for del max, while ordered array proportionally to 1 million and 1 million for insert and 1 for del max. You can see the difference just with two operations, right? What consequent important fact can we also take from this table? Algorithm can be considered as more effective compared to other algorithms if all most often used operations are more efficient. It's usually impossible to have big O constant time for all operations, but trying to have log n big O for most operations and avoid slower ones like n big O would be ideal situation for considering algorithm as very efficient. We will see similar situations later for other groups of algorithms. One extra thing about binary heaps. Using it, you can effectively implement sorting of array, if needed. Small remark, key values in binary heap do not need to be fully in sorted descending order towards its leaves, level by level. For example, you may have higher key on a tree's leaf than key somewhere halfway from a root to another leaf. It's possible for different tree branches though. Remember, all that matters, parent's key is always not smaller than children's keys. To make fully sorted array, you need just to repeat n times del max operation, where n is number of items in binary heap. After each del max step, you put the largest item to the end of the array before removing it. You just don't need actually to remove it from array implementation. Just decrease number of items in binary heap. On the next step, maximum item among the rest will be found and put at a new end, and so on. Eventually, you will have sorted array instead of binary heap, and order of growth will be n log n. and steps of deleting max element with its cost of logarithm n. Such order of growth for so-called heap sort algorithm comparable to ones of merge sort, quicksort algorithms discussed in video What Algorithms. Actually, one last thing I want to add regarding binary heaps. They may have two distinct implementations, maximum-oriented and minimum-oriented. First implementation we have just discussed with the maximum key at the root. Second implementation is for the opposite task, to find minimum element. Logic of work will be similar, but with opposite rules and orders, like minimum key to be at the root, etc. Let's wrap up about second group of algorithms. They can be decomposed to subtasks, and subtask requires to periodically know the largest or smallest element in dynamically resizable set. We mentioned just two use cases out of lots of others. Find m largest or smallest elements in a set of n items, and event-driven simulations with events ordered in time. Binary heap data structure is effective for implementing priority queue, which solves effectively mentioned subtask. We discussed how effectively binary heap is constructed in terms of path from root node to any of its leaf, height of a tree. We discussed in details insert and delete operations with their order of growth. Actually, insert and delete operations contain brilliant algorithms within them for effective result in terms of runtime. We also mentioned that most effective algorithms should try to implement most often used operations to be of logarithmic order of growth. Also pay your attention that even though abstract API contains simple, intuitively easy to understand few functions, like insert and delete, hidden part with implementation has not so obvious to guess algorithms based on binary tree in mind, packed certain way with an array structure. Such implementation is done for the purpose of optimal execution in terms of time saving. We just finished our 2 parts video Why Algorithms. In this video we have covered following topics. Reasons to study algorithms. First, algorithms are surrounding us in daily life. Second, intellectual stimulation in understanding design intent. Third, to be a professional programmer and beat job interviews. Fourth, to deeper study nature through software simulation. Fifth, for fun and profit. Then we discussed term API, which is abstract declarative functionality announcement, which allows to hide actual implementation and build reusable libraries. Then we moved to abstract priority queue API, which allows to retrieve maximum or minimum element from a queue, and corresponding effective implementation through binary heap data structure. Such structure fits in array representation, but has complete binary tree in mind underneath. I have quick announcement that there are few add-on complementary optional videos on the top of this one, if you want to briefly know about several other very often used in computer science abstract APIs and corresponded very optimal real implementations, algorithms and data structures. First one is the key value abstraction, heavily used for information search. Another one is graphs, also used in lots of use cases. You are very welcome to watch them as well and unleash your imagination. Hope you enjoyed this video and will watch optional add-on videos as well. See you!